Key to understanding Earth's evolution is to look at how heat is conducted in the deep lower mantle, a region some 400 to 1,800 miles, or 660 to 2,900 kilometers below the surface. The lower mantle sits on top of the core, where pressures range from 230,000 to 1.3 million times the pressure at sea level. Temperatures are like an inferno, from about 2,800 degrees Fahrenheit or 1,500 degrees centigrade to 6,700 degrees Fahrenheit or 3,700 degrees centigrade. Carnegie researchers with colleagues have for the first time been able to experimentally simulate the pressure conditions in this region to measure thermal conductivity using a new measurement technique on the mantle material magnesium oxide. The researchers squeezed magnesium oxide samples between two diamond tips in an anvil cell up to 600,000 times atmospheric pressure at room temperature and measured their thermal conductivity. The new technique allowed the researchers to measure the thermal properties of the material from the change in the reflectance of the material's surface, thus avoiding the need of contacting the material as required by conventional techniques. They found that heat transfer is lower than other predictions, with total heat flow across the Earth of about 10.4 terawatts, which is about 60% of the power used today by civilization. They also found that conductivity has less dependence on pressure conditions than predicted. The atoms of the major mantle materials are solid solutions and are in a disordered arrangement which affects the way they conduct heat. Until now, the effect of this disorder on the way heat was conducted could only be estimated with experiments at low pressures. The pressure dependence on thermal conductivity has not been addressed in disordered materials before. In addition to finding that heat transfer is lower than other predictions, they also found that conductivity has less dependence on pressure conditions than predicted. The results provide important bounds on the degree to which heat is transferred by convection as opposed to conduction in the lower mantle. The results suggest that this technique could really advance other high pressure and temperature studies of the deep Earth and provide a better understanding of how Earth is evolving and how materials act under the intense conditions. The research is published in the August 9th online journal, Scientific Reports. With the independence for nimble pursuit, Carnegie scientists tackle some of the most profound challenges in modern science, fundamentally changing what is possible for us, our planet, and our universe.